at how total internal reflection is attained. As we've said, in fiber optics communication, we have core and we have cladding. This is N2, this is N1. N1 refractive index of core, N2 refractive index of cladding. And we've said again that N1 must be greater than N2 for refraction and once again for total internal reflection to happen. So again, let's assume this is our normal. This is the interface between these two medias. If we have a ray here of light and it undergoes refraction, you see we have a certain angle from the normal. It undergoes refraction. What if we increase this angle away from the normal? If we increase the angle, the bending goes towards the interface. One thing that is important for us to understand is the principle of refractive index of core being greater than the principle of refractive index of cladding is the one that actually enables our ray to bend towards the interface, and that is what we want. If the refractive index of core is less than that of cladding, our ray will not bend towards the interface. It will bend away from the interface, and that is not good for fiber optics communication. So if I draw a second ray here, let's assume we have a second ray which actually is a little bit more than the original one. You see, you're going to have another ray here. If we go for a third ray, let's say something here, this one is going to bend towards the normal completely. So as we increase the angle, the incident angle of our ray, as we increase the incident angle from the normal, as the angle keeps increasing, our reflected ray, or our refracted ray, actually not reflected, our refracted ray keeps coming closer and closer to the interface. There is an angle that is known as critical angle. Critical angle. There is an angle that is known as critical angle. Critical angle is that angle where if light is shined towards the interface of core and cladding, it gives an angle of refraction of 90 degrees. If we talk about an angle of refraction of 90 degrees, it means from the normal, that angle is going to be this way. It means if we apply our incident ray or incident light at an angle equal to critical angle, our ray is going to align itself completely along the interface. That is critical angle. So if shine light, this is the interface. Once again, if we shine light at an angle that is greater than critical angle, our refracted ray is going to align itself. This is our incident ray having an angle of critical angle. Our refracted ray is going to align itself to the interface. This is a very important principle. And as you can see, if we increase our angle, if we make the incident angle go something above critical angle, it means our ray that is refracted is going to come back inside the core. Because as we increase the angle above critical angle, the refracted ray also keeps bending and bending and bending. Initially it was away from the interface, close a bit. As we increase more, when we are at the critical angle, it aligns with the interface. If we increase the incident angle above critical angle, our reflected ray will emerge. Our refracted ray will emerge like this if we increase the critical angle. Or if we make sure that the angle that we have now is more than the critical angle, the refracted ray is going to bend inside the core. And that is what we call total internal reflection. Total internal reflection is that property whereby if light is applied within the material medium, it is going to keep bouncing within the medium. So as we can see here, at the end, if we make sure that our incident angle is above critical angle, we are going to have something like this. This is the ray of light. As you can see, it is bouncing back and forth within the core. If this is cladding and this is cladding, our ray is going to remain confined within the core. And that's how, and that's why fiber optics can transfer light signal to a very far distant end. Because light is confined, it is not allowed to escape from the fiber optics core. So we must make sure that our incident angle is above critical angle. Thank you.